Bonjour tout le monde, je m'appelle Raphael et aujourd'hui nous analyserons les données de la mission Apollo 11 ensemble avec Java, Redis, and Vector Similarity Search. And that's my cue to go back to English. That's all the French that I had. I'm sorry for that, all right? Guys, I always like to start my presentations with a little bit of context or a little bit of a story of how we got here today. And today is not going to be any different than that, all right? So I want to show you all this website that was put together by this engineer called Ben Feist, who is now working at NASA, where he basically synchronized a lot of data of 3 different Apollo missions, so Apollo 11, 13, and 17. And if you click here, for example, on T-1 minute, it will take us back to 1 minute before the launch of the rocket back in 1969. Let me mute that for a second. And you can see that we have the transcriptions of the mission, 200 hours of transcription here. You have 200 hours of audio between the aircraft and the mission control as well. You have a lot of channels that you can listen to from the mission control itself. He also synchronized videos and photographs. So that's an amazing job that they did here for 3 different Apollo missions, all right? And you can even like jump forward. And one of the things that you can do here is actually search through the transcripts. So he provided that button here, basically, that give us the search capability. And if we search for something such as small step for man, we can see that we matched the moment in which Armstrong said that when he first stepped on the moon. And if you click on that, it's going to take us there, and you can listen to him saying that. Beautiful. Right? But here we have 200 hours of audio. And basically, if you want to learn more about these transcriptions, about everything that they did, and you don't have 200 hours to listen to everything, and you don't know exactly what you're looking forward to finding, it's actually a little bit difficult, right? If I didn't even know what Armstrong had said, I would already have a hard time finding it in the middle of this transcription. So for example, if I had searched for small step for human instead of man, you can see that I'm not matching anything here, all right? So what if instead of searching through exact keyword matching, we could search through meaning, all right? And that's going to be our objective of today. And going back to the presentation, all right, the objective of our mission today is going to be searching for something like that's one small step for a human, one big jump for humanity, and still being able to come across that's one small step for man, one giant leap for mankind, because we want to search for meaning and not only exact keyword matching or full text search. All right, and how we're going to do that is with vector similarity search. And let me know, could you raise your hands if you've done vector similarity search before, or if you know what it is? All right, most people don't know. That's good for me because I'm going to explain it, and it's not going to be boring for you because you don't know what it is. All right, to understand it, I want you all to think about all the planets of the solar system. All right, and then I'm going to ask you this question, that is, what's the most similar planet to Earth? Any guesses? Does anybody want to guess? What's the most similar planet to Earth? Maybe Mars, maybe Venus, right? Well, it depends on which characteristics of the planets we're actually comparing, right? So if we're talking about temperature, for example, then Mars is the most similar planet to Earth. But if we're talking about mass, then Venus is the most similar planet to Earth, all right? And you can actually see that mathematically, because if you trace a line and then divide this line in 1,000 equal parts, going from -500 to +500, and then place all the planets of the solar system on this line based on their average temperatures, just by looking at it, we can already have an estimation of how similar they are based on their temperature. And if we trace lines between those points, we can see mathematically how similar they are based on their proximity on this line, right? So you can see that Earth, for example, is just 50 units away from Mars, while Mars is 45 units away from Jupiter, all right? So Jupiter is 95 units away from Earth, meaning that Mars is more similar to Earth in terms of temperature than Jupiter is, right? But if you're talking about, let's say, colonizing a different planet or doing more with that, we need to also consider other characteristics of our data, or features, or dimensions, all right? And I want you all to remember that word for later on, dimensions, all right? And to do so, we will also consider the mass of these planets. So let's trace another line, also divide this line into 1,000 equal parts, going from -500 to +500, and then place the planets on this line as well based on their mass, normalized from -500 to +500. All right, and what we end up with is a coordinate system with two axes, one representing the temperature and the other one representing the mass. And if we connect the points between those two lines, we end up with vectors. All right, so you can see that on the top left side, we have Jupiter, the vector that represents Jupiter, with two numbers there, two dimensions or two characteristics. On the bottom left side, you have Saturn and Uranus, and on the bottom right side, you have Mercury and Venus. And I removed the other planets from this to not have a lot of things in the image right here. All right? And then, if we still want to see how similar those are to each other, we can still do by tracing a line among them. So if you want to see, for example, how similar Saturn is to all the other planets in this vector dimensional space, we can trace a line between Saturn and all the other planets. All right? And the name of this technique is called the Euclidean distance. That's the Euclidean distance between those vectors. Okay, so you can see that Uranus is the most similar planet to Saturn in terms of temperature and mass, because this is the most close to Saturn in this dimensional space right here, while Jupiter and Venus are the ones that are the furthest, meaning that they are the least similar ones to Saturn. All right, but that's not the only way we can actually calculate the distance among vectors in a vector dimensional space. Another way of doing that is by calculating the cosine similarity. Yeah, oh, it went blank now, I don't know why. Sorry about that. And to do so, what you're going to do is trace a line going from the origin of this coordinate system to one of the vectors, in this case, Saturn, and then another line going from the origin to another vector, and look at the angle that is formed between these two lines. All right? You can see that the angle that was formed in this case was 18 degrees. All right? While the angle that is formed between Saturn and Mercury is going to be much higher, being of 60 degrees, meaning that Mercury is more different than Uranus when compared to Saturn. All right? So far, so good? Okay, and if you keep going, you can even see that Venus is even more distant to Saturn than Mercury is, meaning that it's less similar to Saturn. All right? Okay, so let's just recap everything that we've seen so far. So we saw that a vector is a numerical representation of data. We saw that vectors that are closer together in a vector space model are more similar to each other. And we saw that their proximity is calculated using Euclidean distance or cosine similarity. There are other techniques as well, but today we're going to be looking at these two only. You're going to understand why later. All right, so where does AI fit in it? Because most people are talking about vector databases nowadays in conjunction with AI, all right? And to understand where it fits, we got to look back at all the vectors that we saw so far, because we only looked at 9 vectors with 2 dimensions each. And these 2 dimensions could easily be represented as numbers, right? So mass and temperature. But what if we were talking about unstructured data, such as text, images, audio, videos, or you name it? There is no way of representing this data as straightforward numerically, all right? And what you're going to do to do so is we're going to use embedding models. Have you heard of embedding models? Can you raise your hands? All right, just a few people. So embedding models are basically, in a rough explanation, a machine learning algorithm specialized in converting unstructured data into numerical representation, meaningful numerical representations. In this case here, I have the example of using Ollama or OpenAI, but you could use Vertex AI, you could use any embedding model, one from Transformers, Hugging Face, for example. And I'm going to run this animation array. You guys are going to be surprised how good this is. Basically, I'm going to feed this text to my embedding model, and then I'm going to store this embedding in a vector database, which in this case is Redis. Let's watch it. Vector, storing, beautiful, thank you. And yes, that's the vector database we're going to be using today. We're going to be using Redis for a variety of reasons. The first one is because it's the fastest vector database out there nowadays, according to our benchmarks. We compared Redis to the most popular vector databases out there, but not only the one that offers the highest the lowest latency, but also the one that offers the highest throughput, because Redis can scale to 1 billion vectors without penalizing latency. As you can see, we can still keep 90% precision with a median latency of 200 milliseconds, or 1.3 second median latency for 95% precision for 1 billion vectors. Right? And you guys know that 1 billion is a crazy number, right? You've seen those videos where 1 billion is compared to a million. 1 billion is like, takes many trips around the Earth and all these things. It's a lot of vectors, all right? You can scale very well. So what we want to do is we're going to get all the communications from the transcriptions. We're going to vectorize these communications, and then we're going to compare them in the vector dimensional space inside of Redis, so that we can find if something that the user sends, such as the query that I want to send, that's one small step for human, one big jump for humanity, can match something in the database. All right? So let's recap what we've seen so far one more time. So basically, we saw that embedding models are algorithms that transform unstructured data into meaningful numerical data. In other words, vectors. And vector databases are used for efficiently storing and retrieving these vectors based on their proximity in the vector space model. And something else, we also saw that Redis is freaking awesome, right? As I'm going to show later on as well. Right, so let's talk about this rocket that I brought right now, all right? Are you guys familiar with that? That's the Saturn V. Do you all know how it works? Not really? All right. So basically, this is a 3-stage rocket where you have the first stage coming from the bottom to this part, and it's basically made all of fuel, all right? And then you have the second stage going from this part to that other part, which is also made basically of fuel. And then you have the third stage, that is this part here, that is also made of fuel. And then you have the payload on the top, where you have the lunar module inside of this cone. And then you have the command and module service on the top here, where the 3 astronauts would spend most part of their journey inside. And on the top, you have the escape launch system that was responsible for taking the command module away in case the rocket exploded. All right, so their survival chances were risen, basically. So what happened, and I'm going to make some analogies now, is once that rocket lifted off of Earth, the first stage would be ignited, all right? And in my analogy, the first stage is the JVM, because we're not getting anywhere today without the JVM. But once we got to a certain altitude and speed, we don't need this stage anymore. So it was going to be discarded. We can detach it from the rest of the rocket. And it doesn't mean that we're going to discard the JVM, all right? It's just for the analogy here. And then the second stage would be ignited until it reached a parking orbit around of Earth, all right? And the second stage is going to be Spring and Spring Boot for us, because it's built on top of the JVM, and without it, we're also not getting to the moon this afternoon, all right? But once you got to this parking orbit, we don't need it anymore, so we're also going to detach it and discard it. And then this left part will take a trip around the Earth, basically checking if everything was fine, and if everything was fine, the third stage would ignite as well and take the rocket off of Earth's atmosphere, all right? And then we don't need this part here on the top anymore, the escape launch system, which in my analogy is Kotlin, you know, because sometimes Java is not very good, and then we have Kotlin to save the day, but that's not going to be the case today, so it's going to be discarded. And then the third stage is going to be discarded as well as soon as you get off of the atmosphere. But before that happens, what's going to happen is that this cone here is going to open. Let me try to do that gently. Yes. And expose the lunar module that was hidden in there, all right? And then our astronauts that were in the command module and service, we're going to do a 180 maneuver, dock the command module and service onto the lunar module, undock it from the third stage, discard it in space, do another 180 maneuver, and then keep going towards the moon. All right? I forgot to mention the third stage is Spring Data and Redis. All right? Redis is the library used for connecting to Redis from within Java. All right? And the lunar module is a Spring AI that we're going to be using today as well. All right? But once you got to the moon, what was going to happen is that 2 astronauts, in this case, Buzz Aldrin and Neil Armstrong, were going to get inside of the lunar module, and then they were going to descend onto the lunar surface with that little engine that you probably cannot see right here. All right? But once they got there, Michael Collins would stay inside of this part, taking many trips around the lunar orbit 31 times, to be more precise, if I'm not mistaken, while the other 2 astronauts were down there doing whatever they had to do, maybe dying because they didn't know if they were going to be trapped onto the moon. All right, and once they were done with collecting rocks and playing around, jumping and everything, placing the flag, they were going back together into the lunar module, and then the part of the top of the lunar module would also ignite its engine, take them back to the lunar orbit, and then they're going to do the rendezvous and reconnect with the command module and service. Both of these astronauts would get back into the command module with the rock samples that they collected from the moon, and then they're going to start their trip back to Earth. All right? Once they got closer to Earth's atmosphere, they're going to discard the service module that only contained oxygen, water, things that were responsible for their survival in space, and only this part here would re-enter the Earth's atmosphere. All right? And this would splash into the Pacific Ocean. That would be then collected and recovered by the Navy Army with our astronauts inside, hopefully alive, with the rock samples hopefully intact. But basically, we have all of this rocket to return only this thing right here. And let me ask you, have you been to the Cité de l'Espace in Toulouse? Because they have one capsule like that from Apollo 9 there. I've been there like 6 years ago. If I'm not mistaken, I have a photograph inside of it. That's amazing. That's a great museum. If you guys haven't been there, but you probably have because you're all French, right? So but basically, I told you all this story because I wanted to get to this part here, because in my analogy today, this is going to be Redis on Spring, all right? And Redis on Spring is a library that Redis builds basically on top of Spring Data Redis to allow our users and customers to interact with Redis in a more powerful way. Because in the past 15 years, Redis has evolved from being just a cache into a complete database with a lot of features, including vector similarity search, including support for probabilistic data structures, and including support for JSON as a document database as well, and many other features and optimizations. So we decided to build that, and that's what we're going to be using today to get to accomplish our objective. All right, so let me put it here, because it's important. All right. All right, and finally, if we have time, by the end, I'm also going to show you Redis Insight, which is our graphical user interface that allows you to see everything that is happening within your Redis database, just like Mission Control could do with the aircraft. So they were back on Earth, and the aircraft was in space, and they could still monitor whatever was happening inside of the rocket or the command module and service here and communicate with the astronauts and everything else. All right. So let's talk about what we want to build now. So first, we want to collect the data, basically the transcriptions. Then you want to load this data into Redis and vectorize the utterances. And finally, you want to query that data from Redis efficiently by doing vector similarity search. All right? The data was easy to collect, first of all, because NASA provides all of these transcriptions in a PDF that you can find online very easily on their website. But not only because of that, but also because Ben Feist, that engineer that I showed you in the beginning, he also made this data available on his website that I was able to easily scrape off and start using. Not sure if that's legal. I'm sorry if it's not, but that's what I did. But basically, what you have here, and I have this fancy clicker now that I want to show off. Oh, look at that. Is basically the timestamp of the mission, the utterance itself, oh, sorry, first the speaker, in this case, Neil Armstrong, and finally the utterance itself, the communication, what he said. All right, so we want to load that into Redis and then create that back efficiently later on after vectorizing each of these communications. All right? And how are we going to do that? With something that you're all familiar with. Basically, Redis on Spring is built on top of Spring Data Redis. And if you have used Spring Data before, you have used entity classes. In this case, we're going to do something very similar, but instead of annotating our entity class with @entity, we're going to annotate it with @Redis hash, meaning that we're going to store a hash inside of Redis, all right? If you wanted, you could also store a JSON instead of Redis, and in that case, you would annotate that with @document instead, right? Then you're going to have our ID. In this case, it's going to be prefilled with the timestamp, but if it was empty, it was going to be created automatically by you by Redis on Spring as an UL ID. all right? And finally, we're going to use these annotations in a more specific way, which is the @index annotation that is used for telling Redis on Spring that you want to create indexes and schemas inside of Redis so that we can query data, and in this case, not vectorize data, efficiently later on. Query or filter or sort, whatever you want to do with that, all right? But we want to vectorize the data, so we're going to do something a little bit different. After, we also create the repository just the same way you're already familiar with, but in this case, extending that with Redis Enhanced Repository, right, instead of JPA repository. Okay, and the two annotations that I'm going to use, they're also provided by Redis on Spring. The first one is the @vectorize annotation that is basically going to vectorize whatever is in this field for us, right? Using an embedding model that in this case, from this example specifically, is going to be the default one provided by Redis on Spring, which is one from the transformers Hugging Face, all right? And we have two parameters here. The first one is the destination, which is basically where this vector is going to be stored, in which field it's going to be stored. And the second one is the embedding type, that in this case is a sentence, but it could be an image, because you can also do vector similarity search with images, all right? So you can find similar images, just like Facebook has been doing for, I don't know, a decade at least, when you uploaded a photograph and it automatically matched your friends, right? Based on their faces on the photograph. And then we're going to use this other annotation, that is the @index annotation that I showed you before. But in this case, we're going to have a couple of other parameters there as well. So the first one that I want to show you is the algorithm that you're going to use for searching. That can be either flat, that is more precise, or hierarchical navigable small world, that is more efficient. So that's the one that you should be using when you're dealing with more than millions of vectors. All right? And also, we're going to have to set the dimension of this index that must be based on the number of dimensions. And I told you to remember that word, all right? Because the embedding models, they create vectors of a certain dimensions, of a certain floating points inside. And in the case of the one that is provided by default by Redis on Spring, it's 768 dimensions, and that's why in this example, we're also setting that to 768 dimensions. And finally, you can choose either cosine or Euclidean for the distance metric. And this is the embedded text field, as you can see on line 16. That is an array of bytes, basically an array of floating points in this case. That is going to be stored inside of Redis, our array, our vector. And then you don't have to use the default embedding model provided by Redis. You can also use a different provider if you want to. In this example, I'm using OpenAI, as you can see, with the text embedding 3 large as the embedding model. But you could use Vertex AI, you could use Amazon Bedrock, you could use another model from Hugging Face. You decide whatever you want to use here, all right? The only thing you got to bear in mind is that the index got to match the number of dimensions of the embedding model you're providing right there. So in this case, I'm using text embedding 3 large, and this one creates embeddings with a size of 3072 dimensions, so you got to also match that in our index. And finally, I also wanted to show you this one, because this is for vectorizing images, and if we have time by the end of the presentation, I'm also going to demo something like that for you. Finally, under the hood, what Redis on Spring is doing, it's basically using Spring AI to initialize, to instantiate the embedding models for you. So you don't have to worry about that. That's all abstracted for you. All you have to do is use the annotation. Super easy, all right? So you can see here that we're using the transformers embedding model, for example, to initialize the transformers embedding model provided by Redis on Spring, based on the properties that we set on our vectorized annotation. And finally, we return that is going to be used by Redis on Spring. I'm just showing you what happens under the hood. You don't have to worry about that, right? This is the example for OpenAI embedding model. This is also provided by Spring AI. We're basically using that. We're leveraging that to create the embeddings for you efficiently using Spring AI in a way that you don't have to worry. And finally, we have to query that data back from Redis, all right? And the way you're going to do it is by using 2 beans that are provided by Redis on Spring. The first one is the embedder bean, all right, that we're going to be using for embedding, for vectorizing the query that is sent to the user. So when the user asks a question, for example, we're going to use that embedder to vectorize that and store that in that variable that I called embedding right there, which is an array of bytes, all right? And then I'm going to use this other bean that is called entity string, all right? And you can see that I'm doing of utterance, because that's the class that the entity class that I want to create a stream of, basically. And what I'm going to do with that string is I'm going to filter and sort that. So you can see that in the first line there, in the 5th line, I'm filtering that on the K and N. So K stands for number, and NN stands for nearest neighbors, all right? Because I'm looking for the 3 closest vectors or nearest neighbors inside of this dimensional space inside of Redis. So that's what I'm basically saying there. And then I'm sorting by the similarity score afterwards. And finally, I'm mapping that into a pair where the first element is the utterance itself, and the second element is the similarity score that I want to check afterwards, and collecting all of that to a list. But what I want you to bear in mind is that this is not the Java Streams API, all right? This is the Entity Streams API provided by Redis on Spring. That means that this is going to create a command and send this command to Redis, and Redis is going to do the filtering and sorting on its side. Right? So it's going to be done efficiently by Redis. It's not going to be done on the side of your application. Okay? All right, let's see if it works. I already had the application running. Let's see if it's going to be a demo or a troubleshooting demo. Let's find out. So basically what I want to do is search for that's a small step for human, one big jump for humanity. And let's see what is returned here. Okay, so let's zoom in a little bit. So the first thing that was returned, the closest thing that it found in the vector dimension space was that's one small step for man, one giant leap for mankind. So good so far, right? So far, so good, actually. Pretty good, is it? Kind of, right? Because if you look at the second and the third, they have nothing to do with my query, and they still got a very similar score, 0.06, while the first one got a score of 0.04. So it worked, but it could be better, all right? And going back to the presentation now, where were we? Right here. Once you start vectorizing documents, you're going to realize very soon. Oh, sorry, I wanted to make this joke. Houston, we have a problem. You can laugh now. All right. But basically, you're going to realize soon that once you start vectorizing documents, you're going to find a granularity problem, all right? Meaning that you cannot vectorize something that is too small, neither too long, because you either lose meaning or you have something that has a lot of meaning, all right? And in our case, we were vectorizing things that were too small, basically the utterances themselves. And many utterances that I was vectorizing were basically things like Houston, do you copy? Or Apollo, are you there? Or Tranquility Base, can you listen? Things like that don't really have a meaning, all right? And most of the times, what's actually going to happen is the opposite. You're going to come up with a document that you want to vectorize, and this is going to be too long. In this case, what people usually do, they chunk this document, and they vectorize those chunkings, all right? But for my case, I actually need to aggregate those utterances together so I can get something more meaningful out of them. Fortunately for me, Ben Feist also came up with a table of contents that I was able to scrape from his website. And basically with this table of contents, I could see that everything that came between 2 timestamps like these ones, for example, were related to the same thing. So I could aggregate all these utterances based on the table of contents and get something more meaningful grouped right there. All right, but that's not the only strategy that I want to show you, because I also want to show you this one that is summarization, where I can basically get all these aggregated utterances, give it to an LLM, and ask the LLM to summarize it for me, so that later on, when somebody asks something for my application, I can more easily match it in the vector dimensional space, because the summary is going to be closer to what someone can match, can write, instead of the utterances themselves, all right? And how I'm going to do it, I'm going to use Spring AI here, but not under the hood this time. I'm going to use actual Spring AI, and I'm going to iterate over the table of contents. And then for each one of them, I'm going to basically use the chat response class provided by Spring AI, where I'm going to provide a prompt to it. And the prompt is basically saying you are a helpful assistant who summarizes utterances for the Apollo 11 mission. All right? And then you can see that I have another part of this prompt that is the user message, where I get all the concatenated utterances. So basically the aggregated utterances I provide to it. It's going to return the summary for me. I'm going to vectorize the summary using the @vectorize annotation in a different entity class, and store that in Redis so that I can fetch it efficiently later on. Another technique that we're going to use today is called extraction, all right? So in this case, we're not asking the the LLM to come up with a summary, we're actually asking it to come up with new information that can be helpful for us. In this case, questions. So I'm basically providing the utterances to the LLM and saying, hey, what questions can actually be answered by this data that I'm providing to you? So if they're talking, for example, about dumping waste in space, one of the questions that can be created by the LLM is, how did they go to the bathroom? Or for example, if Buzz Aldrin is talking about the music that he likes to listen, or the music that he took to space, for example, in those old tapes, the LLM can create the question for me that is, what did Buzz Aldrin listen in space? And I know that my users are actually going to ask questions, so that's going to be much easier to match those questions with more precision by doing that technique. All right? And then what I'm going to do is I'm going to vectorize each of these questions and store them in Redis as well. Oh, sorry, I forgot to highlight while I was speaking. Okay, and finally, I'm going to use the entity stream one more time, just like I did before. But now, instead of looking at the utterance class, I'm looking at the utterance question class or the utterance summary class. All right, let's get into the translunar injection, our path to the moon, and also see if that actually works. All right, so I'm going to refresh that, and I'm going to ask, for example, what did Buzz Aldrin listen to in space? Let me ask that, and let's see if that works. Let me hide this one and enable that other one. Oh, no. So this is becoming a troubleshooting demo, guys. Oh, that happened. I don't know why this is happening. Let me stop my application. What I'm going to do is I'm going to stop this Docker as well with all my data. Luckily, I dumped the data. All right, and I'm going to initialize that image again with the data that I had already computed before. And I'm going to start my application once again. And I hope this is going to work. That's a very unique demo for you. I have presented that like 5 or 6 times, and you're the first ones that are seeing that part of it. All right, so it was initialized. Fingers crossed. Oh, it worked. The demo gods. Perfect. Cool. And we can see that it matched 3 questions in this case. All right. It matched the question that is, what music did the Apollo 11 crew play during the mission with a score of 0.23? What music did Aldrin want to play? And what music was played during the Apollo 11 mission? And if I hide this one and show you the summary search, you can see that it matched as well 3 different summaries that I'm not going to read totally, but they're also related to music here. All right? And if you open them, you can see that it gave back to the user the actually aggregated utterances that are related to this summary. All right? But here, it might not be the most efficient way of returning that information to the user because it's still, I'm not really sure how long those can be. Maybe this other one is even longer. Yeah, and then the user has got to scroll or skim through the stacks to find the information that he's looking forward to finding. All right, so what we can do instead is also provide that to the LLM and ask the LLM to come up with the answer for us based on the question that was asked. All right, and that's called RAG, that you probably have heard of before because everybody's talking about it everywhere, which stands for Retrieval Augmented Generation. We're basically feeding the LLM with the related utterances, and then we ask it to answer a question based only on the information that we provide. Right? So in this case, what we were doing was we were embedding the query of the user, we were searching into Redis, and then we were returning the most similar vectors back to the user. All right? But what we want to do instead is actually use Spring AI again to come up with a query, with a prompt where we ask the LLM to answer that question based on the utterances that I provide to it. All right, and then I return that to the user later on. Pretty straightforward. Let's look at that. Let's hope it's still working. All right, so let me refresh this, and I'm going to ask what music did the crew listen to. All right, same question, different wording. Right, let me hide this one and look at this one. Oops, sorry. And I'm going to enable rag as well. That's a very fancy front end. You can see that I'm a front end guy, right? And you can see that in this case, it didn't actually work. It says the provided Apollo mission data does not include any information regarding the music that the crew listened to. Right? Let's ask a different question then. Let's ask, what did President Nixon talk about to Neil Armstrong? Let me see. Let me enable rag. Oh, this time it worked. But you can see as well that it will only work if the data is provided in the utterances. So maybe they haven't talked about the music specifically in the conversations between the mission control and the aircraft, and that's why the LLM didn't provide something back. All right. But in this case, I know that President Nixon actually talked to Neil Armstrong once they were on the moon, and it actually returned something here. So this answer was provided by the LLM based on the utterances that we provided here and the question that we asked right here. So you can see that President Nixon spoke to Neil Armstrong about the historic achievement of the Apollo 11 mission, blah, 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 blah. All right? So basically, it's working. So let me go back to the presentation. Because I want to talk about something else. I still have 10 minutes, which is semantic cache. All right? Because so far, we've been doing caching, but what about semantic caching? So semantic caching works very similar to cache, but instead of looking for exact keys, we're going to look for similar queries inside of Redis, all right? And to make an analogy that here, you guys remember that I talked about the rocket in the beginning, and I said that most of the rocket was made of fuel. So this part was entirely made of fuel, practically. This part was also entirely made of fuel, and each one of them had two tanks, basically inside, one with hydrogen and another one with oxygen. This one had only one tank with a membrane separating both of the elements inside of it, which was probably a little bit more dangerous, but fortunately, nothing ever happened. But that's just to illustrate how critical not only the fuel was, but also the weight of the spacecraft, all right? And in my analogy here, LLM calls, they might be costly, and they also might take time. All right, so what we want to avoid is going to the LLM all the time. So basically, if you ask, how did they go to the bathroom? And you ask, how did they go to the toilet? That's basically the same question, right? With different wording. So what if we could actually vectorize our question and store it in Redis alongside the answer? And then when you ask your question, instead of going to the LLM right away, we could go to Redis, try to match questions that have been asked before. And if we match something that is similar enough, with a threshold that we can set, then we return that answer instead of going to the LLM, spending money, and waiting more time. All right? So the way we're going to do that is by creating a new entity with Redis on Spring, which is in this case going to be the search semantic cache. And we're going to store on that entity the query that is going to be annotated with the @vectorize annotation, and also the answer alongside to it. All right? And then before we actually go to the LLM, we're going to Redis and see if we can match that question if it has been asked before, something similar. All right, and let's see this working now. And basically, I have already asked, for example, what did Buzz Aldrin listen to, right? What did Buzz... Before I do that, let me go to Redis Insight here. Let me zoom in a little bit. So this is the graphical interface I told you about. Let me refresh that. And you can see that I already have some queries cached in my semantic cache. I'm going to delete them. That's a very cool tool that you can use to interact with Redis in a more straightforward way. It also allows you to use the command line interface here. It allows you to create new keys, to look at whatever you have. So for example, you have the utterances here. I can open that, and I can see the vector that was created here. I can see the speaker. I can see the text that was vectorized, and so on. But now that I cleaned the semantic cache, let's go back to the application, and let's ask, what did Buzz Aldrin listen to? And let me ask that. All right. And I'm going to click on Enable Semantic Cache. And if nothing shows up, it means that nothing was matched. All right, but now let's ask something similar. What did Buzz Aldrin? Let's see here. Let's see if it works with that one. Let me enable Semantic Cache again. It didn't work. Let me ask a different one. How did they go to the bathroom? That's a bit longer. All right. Nothing matched because we haven't asked anything similar, but now let's change bathroom to toilet. Same meaning, different wording. And if I click here, you can see that this time it matched. Right? So it matched how did they go to the toilet with a similarity score of 0.06. So basically, you can set a threshold of 0.1. Anything that matches that is smaller than 0.1, you can return that instead of going to the LLM and asking the LLM to process your query again. All right? And we can also, since we still have 5 minutes, I can also show you this. That is the image, the vector similarity search for images. And what I want to do is I have some photographs here, for example, this one, and we can I actually got all the photographs that were in the Apollo 11 Apollo in Real-Time website. I vectorized all of them. I inserted them into Redis using Redis on Spring as well. And, well, let's see if we can find an alien in the middle of them. Right? So let me ask that. OK, display image search. Oh. And it found those images in these two images that are similar, and also others that are not that similar, because I asked for a certain number of neighbors. But you can see that this one had a similarity score of 0.09. Even though it was a different image, it was still able to match that one. But if we do with a real one, let's say this photograph of the Earth, let's upload this one. You can see that it matched other photographs there, all right, with a similarity score that is still very high, 0.13. And so on, many different photographs of the Earth that they took during the mission. Or if you want, we can also take a look at the rocket, and let's see if we can match any photographs like that one. And you can see that it matched as well based on how similar those photographs are to the one that I uploaded here. All right, and all of that done with only 2 annotations, basically. There is the @vectorize annotation and the @index annotation, and 2 beans, that is the embedded bean and the entity string bean. That's all you need to start vectorizing stuff from within Spring Boot and start searching for similar stuff instead of exact keyword matching or exact file matching. Right? And going back to the presentation, let's recap everything we saw today. So basically, we saw how to enhance search capabilities by using vector similarity search. We saw how to improve vector similarity search accuracy by using chunking, summarization, and extraction techniques. We saw how to improve LLM's responses by using retrieval augmented generation. And we saw how to save how to save money and time dealing with LLMs with semantic cache, especially one that is super fast as Redis. All right? That's basically what I had for you today. My name is Raphael. I work as a developer advocate for Redis since November of the last year. Before that, I was a software engineer for the past 8 years, mostly in the Java ecosystem, also with Kotlin. I have a YouTube channel where I talk about Redis. I also talk about Redis on the Redis YouTube channel as well. And on the QR code, you can find the demo for this application. You can run it yourself if you want in your own computer. And also the slides and my socials and everything else. That's basically it. Thank you very much. Before we wrap up, do you mind if I take a selfie with you all? Is that okay? I like to do that to keep the memory. All right. Perfect. Thank you. Do you have any questions? Do you want to ask a question to the application and see if it retrieves anything? Anything that you're interested about the mission, like how did they go to the bathroom, or how did they drink water, or I don't know. There is one fact, actually, I don't know many people know, but I told you that the lunar module is made of 2 parts, right? And basically, we have 2 engines, the one below it and the one right here below the ascent part. And they had a lot of circuit breakers inside of it, basically those buttons that you push or pull that were very common in the past. And Buzz Aldrin, when he was leaving the ascend module, he accidentally bumped in one of those and broke it. And when he found out later that this was the one responsible for taking off of the moon, so basically they could have been trapped in the moon because of this broken circuit breaker. However, it was pulled, and if he could push that back, they were going to be able to escape the moon. And he had a pen that he was able to use to push it back inside. And that's a pen that he carries with him until today, everywhere he goes. Sometimes punching people. I don't know if you saw this video of him. Yeah, but that's basically it. Do you have any questions? No? All right. Perfect. Thank you very much.